Good evening. I would like to take the opportunity standing in front of here to thank Lev Weidman and also others behind the scene for taking this initiative of celebrating the 50th anniversary of the Aharonov-Bohm effect. I think it has been really marvelous so far. So whenever reference is made to the Aharonov-Bohm effect, either a two-path interferometer or a ring-shaped interferometer is what comes to my mind. And presumably this is also true for many other condensed matter physicists in the audience here. Today what I would like to do is, however, highlight a straightforward but maybe not as well-known instance where the Aharonov-Bohm effect is actually at work in K-space rather than in real space. And this instance occurs in so-called artificial crystals, where people have been trying to modify the band structure and the dispersion of electrons in order to tailor the properties. And maybe the most well-known example of that is a vertical superlattice, where we stack semiconductors with different properties on top of each other, and where this modifies the optical properties and the electronic properties. And these are no longer controlled by the individual semiconductor layer, but rather by the periodicity and also by the coupling between adjacent quantum wells. Well, an artificial crystal is essentially a generalization of that, where we try to tailor the band structure in all spatial degrees of freedom. And as you may imagine, it's very difficult to do that in 3D. So it's nice to start from a two-dimensional electron system where electrons are forced to move in a plane so that we only have to take care of 2 dimensions. And so if we have a two-dimensional electron system and expose the electrons in addition to an external imposed periodic potential, that's precisely the context where two-path interference occurs in K-space. And I would like to demonstrate that to you in the transport properties of such systems. Now, my first slide could really be taken from a textbook of physics, so I apologize for the experts, but I think it might be valuable for the students among you in the audience. So my starting point is a two-dimensional electron system. These electrons reside in a gallium arsenide quantum well, for instance, and the dispersion of these electrons in x and y direction is parabolic. Now, if we force the electrons to move in a periodic potential that varies in one spatial dimension, then there's a dramatic change in this electronic dispersion. And basically, as we all know, what happens is that the period of this periodic potential defines new Brillouin zone boundaries. At these boundaries, Bragg reflection may occur. Gaps may open up. The strength of these gaps depends on the strength of the modulation potential. And there may also be gaps at higher order Brillouin zones. This just depends on the Fourier content of the modulation potential. Now you can, of course, repeat this game also in more dimensions. And here is the situation for a two-dimensional periodic modulation. It becomes more richer just because you have to take care of more spatial directions. Now, when we fill this system with electrons up to a certain level, we have a Fermi energy. And if we now start to turn on a magnetic field, the following happens. First of all, what we have in K-space is, and since we are interested in transport, I'm always going to focus what occurs at the Fermi energy. So in K-space, we have this Fermi contour, and in a magnetic field, the electrons will start to move on contours of constant energy. So the electrons at the Fermi energy will start to execute this Fermi, orbit, this circular orbit, in a certain direction that is actually dictated by the direction of the magnetic field. And we all know that if a complete revolution is performed, then the wave function just has to pick up a phase factor that is equal to 2 pi or a multiple of that. And this restriction actually gives rise to quantum oscillations in a number of different properties. One of them is, for instance, the magnetic susceptibility, where we refer to this as the Haas-van Alphen effect. And there's also the electrical conductivity that will show quantum oscillations, and there we call it the Shubnikov-de-Haas oscillations. And these oscillations, they are periodic in the inverse of the magnetic field, and that just follows from the fact that in real space, if an electron executes this orbit, it actually does the following. The orbit in real space is exactly identical to this one in K-space, except that it is rotated by 90 degrees, and it is also scaled. It's scaled by the square of the magnetic length, a length scale that appears as soon as we turn on a magnetic field. It only depends on fundamental constants. It's essentially equal to the square root of h bar divided by the product of the elementary charge and the magnetic field. And so if we calculate the phase, the phase that is accumulated in the course of executing this real space orbit, it would be equal to the area of this Fermi orbit, the fourth order of the magnetic length times the magnetic field. We divide by the elementary flux quanta, and maybe a factor of 2 pi is missing there, and then we just end up with this phase factor here. So we get 1 over b periodic oscillations in these quantities that are inversely proportional to the area of this Fermi contour. So if we now go to 1D modulation, then what happens is that the Fermi contour has changed dramatically. We now get different types of Fermi contours. We get open runaway contours that are not closed and therefore will not contribute to quantum oscillations. And then we also get, for instance, in this particular situation, this closed orbit here, which is much smaller in area, covers a much smaller area compared to the original Fermi surface. So we expect that the magnetic susceptibility and also the electrical conductivity will show quantum oscillations with a very different periodicity. You can do this then again for 2D, and there it just becomes more rich. You essentially have a number of different closed orbits that may form. And of course, I should point out that the shape of these orbits depends very critically on where the Fermi energy is. So as you change the density, the shape of these closed orbits that form in K space at the Fermi energy will change with density. All right. Now, how do we actually produce such samples in where the electrons are exposed to a periodic potential? Well, I will go over this very quickly. Basically, what we do is the following. We have our two-dimensional electron system that resides in a gallium arsenide quantum well, and this quantum well is buried underneath an aluminum gallium arsenide layer, and it's typically about 50 nanometers below the surface. Then we deposit the resist layer on top of this crystal, and we pattern this resist layer by basically drilling holes in it with electron beam lithography. We then deposit the metal on top of it, and you may imagine that if we apply a voltage difference now between our metallic gate and our two-dimensional electron system, that we are going to create a periodic modulation of the density. Just because the metallic gate is periodically displaced differently here where there's PMMA and where there's no PMMA. That's actually only one source of modulation produced by this metallic gate. It turns out that the more important one is actually the fact that when we cool down our sample, the thermal expansion between the metal and the semiconductor is very different, and also between the PMMA and the semiconductor is different. So this metallic gate, as well as the PMMA, which is the resist layer, act as a periodic stressor, and since gallium arsenide is piezoelectric, it's going to produce, at the level of the two-dimensional electron system, a modulation of the potential. And it turns out that this effect is actually much stronger than the effect that we can produce by applying a voltage to our gate. So typically, the samples that we look have a variation of the potential landscape that is on the order of a few % of the Fermi energy. Now, the effects that I'm going to show here rely decisively on the fact that the periodicity of this lattice is comparable to the Fermi wavelength. In our samples, the Fermi wavelength is on the order of 40 nanometers, and the periodicities that I'm going to look at is 100 nanometer. Also important is that there's little disorder. Disorder will smear all the effects that I will discuss, so we better take a good sample. And the samples that we received for this particular purpose come from the Weizmann Institute, from Vladimir Romansky, and have a disorder that is very small. We have a main free path as large as 50 microns, so the electron can flow ballistically over this distance. Okay, so now we can go ahead and take a first look at how such an experiment looks like a transport experiment. So we have the sample, it's shaped in a hole bar, we have a source and a drain contact, we send the current from the source to the drain, and we measure the resistivity by measuring the voltage across these two potential probes in the direction of the current flow. And if we do that and plot the resistivity as a function of the magnetic field, we get this very rich spectrum of oscillations. And you see there are some beatings there, and clearly this is not just a single periodicity that we observe here, there is much more to it. And since we are expecting 1 over b periodic oscillations, we better replot this data on an inverse magnetic field scale. And if we do that, it's more clear to see that we have oscillations with different periodicities available in this data. So here I highlight two different cases, at small magnetic fields, for instance, we have these oscillations with a large periodicity, and at larger magnetic fields, we get these oscillations with a much smaller periodicity. So where do these oscillations come from? Are these indeed the closed orbits that we expect for this 2D periodically modulated system? Well, let's take a closer look. The best way to reveal the 1/b periodic oscillations is, of course, to take a Fourier transform. And if we do that, we see that we get a whole zoo of peaks in this Fourier spectrum. What I'm plotting here at the bottom is the inverse of this 1/b periodicity, and at the top I'm actually showing the area that would correspond to this particular peak in K-space, and it's expressed in units of the first Brillouin zone. Now, there are many features here, and I would like to highlight the following. If we modulate our system in 2D, then we get a number of closed orbits, but you notice that all these orbits are actually smaller than our first Brillouin zone in the system. So we expect to see these oscillations all in this area here that is below 1 on this axis with units of Ka squared. We get, however, many oscillations that correspond to areas that are much larger than our first Brillouin zone. So obviously I'm not observing mainly these orbits. There must be other closed orbits in the system that produce these 1/b periodic oscillations. So clearly there's some important ingredient in my picture missing, and this important ingredient is well known in metal physics. It's basically magnetic breakthrough, and I will come to it in a second. So one thing that is important to notice is that, for instance, this peak here that we observe, corresponding to certain oscillations with a certain periodicity, actually corresponds to the Shubnikov-de-Haas oscillations of the original system that was unperturbed. So we apparently see not only closed orbits that are defined by this periodic potential that I impose, but also orbits that we do not find normally along the Fermi contours, but for which we would have to cross essentially gaps in between these Fermi contours. So clearly we need to be able to tunnel across gaps in order to account for the appearance of these orbits. And that is actually possible by the mechanism of magnetic breakthrough. And I would like to explain this effect of magnetic breakthrough in a hand-waving argument as follows. Let us consider the 1D case. We had these little closed orbits, we had these runaway trajectories. Now normally the electron in the weak magnetic field limit is only capable of following either this trajectory if it's on this one, or it will follow this closed trajectory. It could form a closed orbit if it would be able to tunnel at this particular location where these two different Fermi contours approach each other closely. So what is happening there? Well, the following is happening. Basically, in the limit of small magnetic fields, we are dealing with plane waves, and there's a large uncertainty in real space. But as we turn on the magnetic field, the electronic wave function is modified, and actually the spatial extent of this electronic wave function is set by the magnetic length. So as we increase the magnetic field more and more, the magnetic length becomes smaller and smaller. It's essentially 25 nanometers per square root of Tesla. And so the uncertainty in real space becomes smaller and smaller. But this means that the uncertainty in K space becomes larger and larger, so that eventually the electron will actually be capable to overcome this discrepancy in K and will be able to tunnel from this trajectory onto this trajectory. And the tunneling this probability for tunneling is actually described by this equation here. It contains the energy gap. It contains delta K, which is this change in momentum space. And it also contains the angle under which these segments of these Fermi contours are, and also the magnetic field via the cyclotron energy. As the magnetic field increases, the cyclotron frequency increases, and you see here that eventually this probability will turn equal to 1. So in the high magnetic field limit, the electron will, whenever it has a chance, it will actually always tunnel. And as a result, in the high magnetic field limit, when it's going to cross all these gaps that were opened up by the periodic potential, it's going to follow again the original Shubnikov-de-Haas orbit that we had at the very beginning where we did not have a periodic modulation. So the fact that it can tunnel now means that there's a whole zoo of closed orbits that we can form. We just take different segments of the Fermi contours, wherever they need to tunnel, we let them tunnel, and we can come up with a large variety of closed orbits. Yet in experiment, we only see a limited amount. So clearly, we need some criteria to identify which one we really see in experiment. And the only way to find out is actually to do a simulation. And the best way of doing it is to do a Monte Carlo simulation where you let the electrons walk along these trajectories. You follow this trajectory until it forms a closed orbit. And then you try with the next electron and so forth. And if you've collected enough closed orbits, you can make some statistics. And you can identify which orbits are the most probable. That's actually what we did for our system. And basically, here are the plots of some closed orbits that we can see in our experiment and that come out of such a Monte Carlo simulation. And the color of these orbits is essentially reflects the probability for these orbits to appear. So in this Monte Carlo simulation, it's obviously going to find many similar versions of this orbit that are just mirrored or translated or that are rotated. And obviously, you need to put all of these orbits in the same bin in order to get the appropriate statistics. Now, these green points that I've marked here on these orbits are actually those points where the electron does not tunnel. And in any of these orbits that I'm showing here, you need as many as 700 segments of the original Fermi contours to construct them. So there are many more tunneling events than there are locations where the electron does not tunnel. Just to give you an idea. Okay, so one thing that we can do in order to help us identify which orbit is responsible for these oscillations in our experiment is actually to change the density. As we move the Fermi energy, these orbits are going to change in size, and presumably this density dependence will be specific for each orbit. So we can do that actually by using an effect called the persistent photoconductivity effect in gallium arsenide, aluminum gallium arsenide heterostructures. You can illuminate a sample with light from an LED, and it's going to persistently change the density. Then if you repeat the experiment that I showed you before, recording the resistivity as a function of a magnetic field, you take the Fourier transform and so forth, and you do that for 100 points, and you spend a lot of time, then you eventually end up with a spectrum like this. So this is a Fourier spectrum of 100 curves, and you see here nicely that there are orbits, that the dependence of the size of these orbits as a function of the carrier density. You can now take your Monte Carlo simulation and do this Monte Carlo simulations for the various Fermi energies that you're covering as you change the density, and then you can identify unequivocally, basically, that, for instance, this particular feature in the data corresponds to these particular orbits. Now you notice that in our data there, and I'm getting to the point of this talk, that there are a number of features in the data that we can actually not recover by just considering closed orbits in our Monte Carlo simulation. So clearly, something more is happening. The physics is even more richer than just finding suitable closed orbits that are either there just because of the modifications in the band structure or that appear that can form as a result of magnetic breakthrough. So what are these other lines that appear in this Fourier spectrum? Well, it turns out that this has everything to do with a two-path interference of electrons in K-space. And a simple example is again shown here for the 1D case. Now, imagine that I have the following situation. I have an electron that is moving on this open trajectory, and when it comes here, it has two possibilities. It can either continue to move along this open Fermi contour, or it can tunnel. If it moves along this contour, then here it has the possibility to tunnel and to eventually form this trajectory. This electron can, however, also take this path and end up at the same endpoint. So clearly, there's the possibility here of a two-path interference. This two-path interference would result in enhanced backscattering, as you can see here. Imagine that the phase difference between this path, maybe I have an animation here, between this path and this path is constructive, then it's going to cause enhanced backscattering of the system. And if the interference is destructive, then there's not going to be enhanced backscattering. So obviously this two-path interference is going to cause oscillations in the resistivity. And so when do we have constructive interference? Well, we have again, we basically have two contributions here to the phase difference for these two paths. One of them comes from the tunneling events, and the second, which is magnetic field independent, and the second contribution comes from the Aharonov-Bohm flux. The fact that the real space orbit is given by this, or the difference between this path encloses an area that is equal by this area in k-space multiplied by the fourth power of the magnetic length. And so that might be an additional source for 1/b periodic quantum oscillations. So here again, I would like to highlight the difference between the closed orbits, where the electron just completes a full loop. This orbit on the right side here cannot be explained as a closed orbit because the magnetic field tells the electron that it can only move in this direction on these segments, and it can only move in this direction on these segments. So the electron cannot actually execute the following orbit. It must be a two-path interference effect. All right. So here's actually the outcome of such a Monte Carlo simulation, where we take into account not only the closed orbits, but also these two-path interferences, and where we keep properly track of phases. Now, you see that it's maybe hard to see that there's a nice correspondence between the experimental data. So what I'm going to do is I'm basically going to slide one over the other, and then you will see very nicely that many of the features that we recognize in our experimental data are also present in the simulation. And in particular, these lines here at small values of the inverse periodicity that are much steeper, that have a much steeper dependence, a weaker dependence on the density, correspond actually to orbits, to these two-path interferences that I was explaining before. And it's only by including these two-path interferences that we can account for this data at this, in this lower portion of the Fourier spectrum. So I would like to conclude by basically telling you that in these artificial crystals, we observe quantum oscillations that originate both from closed orbits that can form as a result of magnetic breakthrough, and that we also, however, observe quantum oscillations that originate from a two-path interference in k-space, and that this accounts for most of the experimental features. I would like to thank, finally, some discussions with Rolf Gerhards, as well as technical assistance from these people here. Thank you.
Thank you very much. Very interesting talk. You have some question? Okay. Please.
You said that there was this Aharonov-Bohm phase for the closed path. But in order to calculate it, you have to go to the real space and see what it is. Could one introduce a direct field in the k-space and calculate and have something like Aharonov-Bohm flux in the k-space?
I always have to go through the transformation of real space. I do not know how to handle this in k-space. But the transformation is simple, and it's general. I mean, it doesn't matter on the shape of the k-space orbit. It just follows from classical equations of motion that you have to rotate it by 90 degrees, and then a dimension argument just tells you that you have to multiply it by the square of the magnetic length.
Other questions? Okay.
If you make modulation sufficiently large, can you really stop the magnetic tunneling?
Experimentally, it's very difficult to reach this limit because it has to do with what was also mentioned by Klaus Enslin, that in these two-dimensional electron systems in gallium arsenide, they're always buried. So the modulation is always weak. It's very hard to really get down to modulation levels that are high enough especially for small periodicities. And ultimately, in the limit of high magnetic fields, you will be able to tunnel, independent of...
Okay, thank you very much.